What if you could just stop fighting fires and actually start preventing them? That's really the big promise of machine learning for SREs. Today, we're going to look at a core concept of supervised machine learning called gradient descent. It's a technique that can help you predict the future of your systems better. Let's dig in and see how it all works. Just imagine this for a second. Your pager goes off, but it's not just because an SLO has already been breached. Instead, it's a warning that an SLO is going to be breached in about 30 minutes. I mean, that's the dream, right? It's about making that huge shift from being reactive to truly proactive. That sort of thinking is what we're going to unpack today. For years, we've all relied on these static thresholds like, alert me when CPU is over 80%, but they get noisy and often lack context. We also have auto-scaling, which is fantastic, but it's still fundamentally a reaction to something that's already happening. If it's even a little too slow to kick in, your customers feel the pain. We need something smarter, something that sees the trend coming way before it becomes a problem. Now, in our last video, we looked at the predict linear function in Prometheus. Under the hood, it's based on a foundational machine learning technique called linear regression. In the simplest terms, linear regression is when you have a whole bunch of historical data points like CPU usage over time and draw a line that best represents that trend. Once you have that line of best fit, you can just extend it out into the future to predict where the next data point is probably going to land. But now here's the problem. How does a machine actually figure out which is the best fit? How do we even quantify what best means in the first place? We do this by measuring the error. For any line we draw, we can look at each of our real data points and measure the distance to our predicted line. Then we square those distances, which is a neat trick to penalize the really big misses more harshly, and add them all up. That final number is our cost. So the best line is just the one with the lowest possible cost. Our whole mission now is to find the very bottom of that cost curve. This process is known as gradient descent. So how do we find that sweet spot, that point of lowest cost? There are two main mathematical paths we can take to get there. On one side, you have the normal equation. Think of this as a direct shot. It solves for the perfect line in one single clean calculation. On the other side is gradient descent, which takes an iterative step-by-step approach. Now here's the absolute key for us. The normal equation can get incredibly slow when you have a large workload. Gradient descent, on the other hand, scales beautifully, which makes it the go-to choice for the kind of complex high-volume data we deal with in production systems. So how does gradient descent work? Let's focus on the intuition here, because I think it's really cool. Imagine you are standing on a foggy hillside and your goal is to get to the very bottom of the valley. You can't see far, but you can feel the slope of the ground right under your feet. The gradient is basically checking that slope to find the steepest way down. You take one step in that direction, and the size of your step is controlled by your learning rate. If you take too big a step, you might overshoot the bottom entirely. Too small, and it will take you forever to get there. You just repeat this process over and over. Check the slope, take a step, until you can't go any lower, and you've arrived. This is gradient descent. Alright, that's enough theory. Let's put this into practice. So our mission is to build a model that can forecast user latency using our normal system metrics. We're going to see how both the normal equation and gradient descent handle some real-world data. Feel free to play around with the notebook to understand the information I've provided. We're just going to look at the important results in this lab. So, let's install our dependencies and visualize the data we have. Cool. I'm sure this looks pretty familiar to any SRE out there. CPU usage is climbing steadily, and network traffic is climbing as well, and then the latency starts to get very noisy and spiky. Our job is to find the signal buried in all this noise. The key research question I have is, can you predict when traffic will cause latency beyond your known threshold? We're going to tackle this with a two-model strategy. Model 1 forecasts just the system load, the CPU, a little bit into the future. And model 2 is a second, more complex model that takes that forecasted CPU load and uses it to predict what will happen to latency. Model 2 is also a very good example of using multiple features in machine learning prediction. So, let's run the code that implements Model 1. These two functions implement both the normal equation and gradient descent, and then we plot them side by side. So because the CPU trend is pretty linear, when we feed this to both algorithms, the blue line from the normal equation and the orange line from gradient descent are perfectly on top of each other. This shows us that for a simple problem with just one feature, both methods work very great. Another interesting thing for you is we can play around with this slider to see how the number of epochs and the learning rate affect the fit. When we train for a small number of epochs, which just means the amount of repetitions, the model does not converge. But larger epochs converge and don't provide any further improvements after. With the learning rate, it's similar. A lower learning rate means a longer time to converge. But a higher learning rate means that you might overshoot. Things get a little more interesting with Model 2, which brings us to probably the single most important thing we learned while preparing this lab. We're only training our model on the baseline data. And the baseline data is a period before the system gets overloaded and latency goes totally off the rails. This is because the relationship between system load and latency is only linear when the system is healthy. The moment you hit a bottleneck or saturation, a tiny little increase in CPU can cause a massive, completely non-linear spike in latency. If you try to fit a line through that whole chaotic period, you end up with a terrible, misleading model. The only way to get a reliable prediction is to train it on predictable pre-saturation behavior. Well, now it's time for the payoff. Let's chain these two models together. Model 1 projects the CPU trend out 30 minutes into the future. We take that predicted CPU value and then feed it into Model 2. Our model, which was only trained on healthy data, predicts that this future load will result in a latency of 318 milliseconds. And that sounds like our warning, right? In theory, we now have a data-driven forecast that trouble is on the horizon, giving us a full 30-minute head start to act before our SLOs are ever breached. Now it's time for the strong caveats. As you've already seen, latency is unfortunately not always related linearly to our other metrics, even in our examples. So our work is not done. We are learning what behaviors can be predicted with the right models. I believe what we truly need here is either ensemble trees or anomaly detection. And yes, we will look at those in upcoming videos. And just to quickly recap, Model 1 used time to predict CPU, and Model 2 used CPU and network traffic to predict latency. By chaining them together, we built a powerful end-to-end forecasting pipeline. This can be a fundamental shift in how you approach reliability engineering. This ability to stop looking at dashboards of the past and to start getting a data-driven view of the future means that you can do proactive capacity planning and set alerts on predicted SLO breaches. You can walk into a meeting and say, we will need to scale in 30 minutes, and here is the data that proves why. Most importantly, it means that you can protect your SLOs by solving problems before they even happen. I encourage you to start thinking about your own problems, your own key metrics, and your own pain points. If you had this ability to predict the future, what would be the very first question you ask it? Thank you for joining me, and don't forget to subscribe to the channel. Peace.